Good day, everybody. In this week's experiment, we'll be working on Lewis structures and the molecular models. We'll first learn how to draw Lewis structures. Based on the correct Lewis structures, we should be able to build molecular models. Since we are not in the lab for this week, we'll skip this step. With the same correct Lewis structure, we should be able to derive the correct molecular shape by using VSEPR theory. So first, let's see how to draw the correct Lewis structure. So, how do we draw correct Lewis structures? To draw a correct Lewis structure, first step, you want to calculate the total number of valence electrons. For example, how many valence electrons does carbon have? It is actually quite straightforward because we can look at the periodic table and find this out. When we look at the periodic table, the group number in the AB system, okay, not 1 through 18, will be the number of valence electrons for the main group elements. For example, when we look at carbon, carbon sits in group 4A. So carbon would have 4 valence electrons. How about nitrogen? We find nitrogen, and it's located in group 5A. So nitrogen will have 5 valence electrons. What about chlorine? Chlorine sits in group 7A. So chlorine will have 7 valence electrons. What about hydrogen? Hydrogen sits in group 1A. It has 1 valence electron. Step 2. Step 2, you want to connect outer atoms, or sometimes it's called peripheral atoms, with the center atom. Using a single bond. You might be wondering, if I give you a formula, which one is going to be the outer atom, which one is going to be the center atom? It turns out it's actually quite straightforward. For example, if you have CH4, carbon will be the center atom. Usually, the first written in the formula will serve as the center atom, except for hydrogen, because hydrogen cannot serve as a center atom. So the first element in the formula usually is the center atom. Do you remember, hydrogen cannot be center atom. I'll give you a few more examples. For example, in chloroform, CHCl3, carbon is going to be the center atom. In NH3, or I'm going to do maybe NF3, nitrogen is going to be the center atom. Okay. What about CO2? In CO2, carbon is going to be the center atom. Step 3. I want you to do the octet for outer atoms. Do you remember the rule for outer atoms is actually quite straightforward. because most atoms will prefer a total of 8 valence electrons. But hydrogen is one of the exceptions. Hydrogen prefers 2 total. Sometimes we call this duet because it's 2 electrons. And 8 electrons, we call this octet. After we do this, we will recalculate the number of valence electrons and find out how many valence electrons are still available. And we will place the remaining electrons, valence electrons, on the center atom. The last step, we'll do the octet for center atom. The octet rule for center atom actually has a lot of exceptions. Okay, so I'm going to write down the full list of this. For example, beryllium actually prefers 4 total. If you have boron or aluminum, they prefer 6 total. But do remember, they can also take 8. 8 is okay for them. For all the other elements in the second row, they will take 8. They can never take more than 8, remember, for the second row. However, for elements in the 3rd row to the 7th row, so I'm going to write it down over here. So for elements in the 3rd to the 7th row, they can take 8 total or more than 8. So let's use these 4 examples listed over here to show you step by step how to arrive at the correct Lewis structure. For example, when we look at methane, CH4, the first step, how many total valence electrons do you have? Because carbon, check your periodic table for this, okay? Carbon has 4 valence electrons, okay? Each hydrogen has 1 because it sits in group 1A, and we have 4 of them because we have subsequent 4. So we find out we have a total of 8 valence electrons for CH4. What about chloroform, CHCl3? Carbon has 4, hydrogen has 1, and each chlorine has 7. We've got 3 of them. So you total it up, it's 26 valence electrons. For NF3, nitrogen sits in group 5A. Again, check your periodic table. Each fluorine would provide 7 valence electrons. We got 3 of them. So it turns out it's also 26. What about CO2? Carbon in group 4A, it has 4 valence electrons. And oxygen has 6 valence electrons. So we calculate this, that gives you 16 total valence electrons. Okay, so that's our step 1. I'm going to color code this So for step 1, I'm going to work on everything in red. Second step, I'm going to maybe change it to blue. All right. So the second step, we're going to connect the outer atoms with the center atom using a single bond. As we just learned, the first is usually the center atom, unless it's hydrogen. So what do you mean center? Center, that means you put it right at the center. And it's connected with 4 hydrogens with a single bond for step 2. So when you write it, you want to make sure this will look a little bit more beautiful. And they are connected to outer atoms, hydrogen. For the second structure, CHCO3, chloroform, we can do this in similar fashion. Carbon is the center atom, and it's connected to the 4 other atoms using a single bond. So you can put hydrogen anywhere. So you have chlorine, chlorine, chlorine. Okay. For NF3, nitrogen serving as the center atom, and I'm going to write the single bonds, the left, right, and the bottom. The question is, can I write 1 fluorine above the nitrogen? No problem. Okay, it's just how I wrote it. For CO2, carbon, I write it at the center, and either side you have 1 single bond. So that's our step 2, which is quite straightforward. All right. For step 3, I'm going to change it to another color. Let's do, we don't have that many color actually. So I'm going to do a black color over here. So for step 3, we're going to do the octet for outer atoms. Outer atoms, look at the rules for outer atoms. If it's hydrogen, if you have 2 total, it's good enough. Okay. Do remember, when we look at outer atoms, we only focus on outer atoms, which means the bonds connected to those atoms. Do remember, 1 single bond contains 2 electrons. So after step 2, all outer atoms, no matter which one you're looking at, this one, this one, this one, this one, this one, this one, no matter which outer atom you are looking at, they all have 2 total electrons. But if it's hydrogen, because hydrogen, when you look at that, hydrogen prefers 2 total. So for step 3, you actually do nothing. You don't want to put the dots surrounding this hydrogen. That would be wrong, because each hydrogen has a single bond connected to it, which means it's 2 electrons already. Okay, so for this structure, step 3 is done. I'm going to put a check mark. For chlorine, though, you're going to put 6 more, because you only, for this chlorine, you only got 1 single bond, which means 2 electrons surrounding this chlorine. You need 6 more. So we're going to put them over here as 3 pairs. Similarly, we can do that for the other 3 chlorines. One common mistake is you're going to put extra electrons for hydrogen, which is wrong, okay? Because hydrogen prefers 2. You have 2 already. We're going to do the same for all other outer atoms. For fluorine, you only got 1 bond surrounding it. You need 6 more. That would be 6 electrons. All right? Okay. So for oxygen, we do the same. Put them in 3 pairs. Again, when you are looking at the outer atoms, look at outer atoms only. Don't even touch the center atom for this step. Okay, so this is done now. This is also done. This is done. All right. What is step 4? Let's go on and use a different color. Let's say we're going to go to red this time. Okay. So number 4, we're going to recalculate. Okay, we're going to recalculate how many electrons we have left. So we place all of them on the center atom. So we do know we started with the 8 atoms over here. Okay, how many have we used to build the bonds? You have 4 single bonds over here. So 4 single bonds would have 8 electrons. Have we used any dots here? No. So we end up with no electrons left. What about the second example? The second example, we started with, look at this, we start with 26 valence electrons. And then we used 4 single bonds that would take 8 valence electrons. Do remember, each chlorine consumes 6 dots, 6 valence electrons. So 3 of them would give you 3 times 6, which is 18 valence electrons. That also gives you no electrons left. Okay. So for number the 3 example, NF3, we got 26 valence electrons left. And how many bonds have we built? We have built 1, 2, 3. 3 single bonds, that's 6 valence electrons. Okay. And we also used the 6 dots for each fluorine. We got 3 fluorines, so that's 18 valence electrons. So when you put it together, we notice we have 2 valence electrons left. Do remember, for step 4, you are going to place all remaining valence electrons on the center atom. That's exactly what I'm doing over here. So those 2 electrons come from the remaining electrons. Let's look at CO2. CO2, you started with 16 valence electrons, and you used 4 electrons to build these 2 single bonds. And you also used 6 electrons to make dots for each oxygen, so that's 12. So you end up with 0 left. So now we know step 4 is done. Okay. What about step 5? Step 5, we are going to check the octet for center atom. Do remember, you need to be 100% sure about the octet rule for center atom, which has a lot of exceptions as we listed over here. So let's use blue over here. Okay. So that's the octet rule and exceptions. Step 5, we're going to check the center atom and see if they have satisfactory number of electrons as described by the rules listed right over here. Okay, so look at center atom. This center atom is carbon. So how many valence electrons does it have? This carbon has 1, 2, 3, 4. So that's 4 single bonds, no dots surrounding that carbon directly. That's 8 valence electrons already. Okay, so for this reason, we do know this is already the correct structure. Okay, so just remove this little dot over here. So carbon has 8 electrons according to the rules. That means this is good. All right, so this means this structure is the final structure because we have completed all 5 steps. Let's look at the second one. The second one also has carbon as the center atom, which is over here. Carbon has 1, 2, 3, 4 single bonds surrounding it and no dots. That's 8 valence electrons. Oh, carbon is happy. So that means for the second example, it's also the final Lewis structure and its correct structure. Okay, let's look at the third example for nitrogen. Okay, how many valence electrons does it have? Nitrogen has 1, 2, 3 single bonds. That gives you 6 electrons plus 2 dots. So that's 8 valence electrons. Hey, looks like this also has octet satisfied. Does it mean everything will be like that so you don't have to do step 5? Of course not. If so, we would not even write out to step 5, right? So let's look at the next example. For this carbon, how many valence electrons does it have? This carbon has 1, 2 single bonds surrounding it, which is 4 electrons, no dots surrounding this carbon. Remember, we are looking at the center atom right now. We don't even care about the outer atoms for this step. So this carbon has 4 electrons surrounding it. Is this good? No, this is not good. Okay, so you need more because carbon needs to take 8 valence electrons. So how do you do it? If you have less electrons than you will be happy with, you actually want to form multiple bonds. So here's how you do it. This oxygen will share this pair of electrons, which means it moves these 2 electrons to the middle to share with carbon. So oxygen does not lose 2 electrons, but carbon will gain 2. Remember, carbon needs 4 more. So we can actually use the other oxygen to move 2 more in the middle to share. Okay, when you share this 2 electrons, you form a covalent bond. So let's represent the whole process. So when you have this carbon, remember on the left side it was a single bond, on the right side it's like this. To remember, over the top you had 2 electrons, but that was moved to the middle to form 1 extra bond. So the single bond becomes a double bond. On the right side it's similar. Okay, do you have to put those 2 electrons on the right side? Can you move it to the top? No problem. Okay, as long as that spot is available. So this will give you the final Lewis structure. So hopefully by now, through these 4 examples, you will be able to draw the correct Lewis structures for your homework, which you need to turn in next week. Next, we are going to learn how to derive the correct molecular geometry or molecular shape based on the correct Lewis structure. So let's write down the 4 Lewis structures we just arrived at. That was for CH4. We had C carbon connected with 4 hydrogens with the single bond as the final answer. And the chloroform has a Lewis structure with carbon sitting at the center connected to the 4 atoms with single bonds, but for each chlorine you have 6 valence electrons surrounding it in 3 pairs. For NF3 you have nitrogen sitting as the center atom with 3 fluorines, each have 3 lone pairs. Each lone pair has 2 electrons. Next we have CO2, which has carbon at the center connected with oxygens through a double bond. To get the correct Lewis structure, first we need to figure out how many electron groups, or so-called what's the steric number for the center atom. Okay, so for the shape, you do need to remember first, when we talk about the shape, usually it's about the center atom. You can talk about the shape for outer atoms, but it's rare. Okay, so usually the shape is the shape surrounding around the center atom. Okay, second, we need to figure out the number of electron groups. Surrounding the center atom. We can just use EG. Okay, sometimes it's also called a steric number. Okay, so what is the number of electron groups or steric number? electron groups, we have different one. Sometimes they are bonds, sometimes they are long pairs. Okay. So remember, it doesn't matter if it's a single bond, a double bond, or a triple bond. They are all considered as one bond. When we count the number of electron groups, they will be considered as one electron group, or steric number for one bond will be 1. So if you have one single bond, this is one electron group. If you have a double bond, it's also one electron group. A triple bond, it's one electron group. Okay. So what is a lone pair? Lone pair is 2 electrons. A pair of electrons, a pair of dots, is considered as one electron group. Okay. So we should be able to count the number of bonds plus number of lone pairs and add it together. This gives us so-called electron groups or steric number. Okay. So let's look at the center atom carbon over here. For carbon, how many bonds do we have? You have 1, 2, 3, 4. 4 single bonds. So I'm going to write SN number is 4 single bonds plus no lone pairs. Usually I want you to write both the number of valence electrons, both the number of single bonds or any bonds, okay, plus the number of lone pairs. Then you get the total. This is more clear because you do know this 4 comes from 4 plus 0. Okay. And similarly, if you look at the next one, for carbon center atom, you have 1, 2, 3, 4. Again, when you look at a center atom, you don't ever look further than that. You only look at what bonds or dots are connected to the center atom. This carbon has 4 single bonds with no dots. So the steric number similarly will be 4 plus 0 because you have no lone pairs. The total is 4. All right. In a little bit, we'll show you how to get the correct molecular shape according to the steric number, which is calculated in such a way. For this nitrogen center atom, the steric number, how many bonds do you have? You have 1, 2, 3. So this gives you 3 bonds. Plus, don't forget about this, you have a pair of dots sitting on nitrogen, which is 1 electron group. So this gives you 4. But this 4 comes from different sources. It's coming from 3 plus 1. For carbon, the SN number, you have 2 lone pairs, 2 double bonds. Each double bond is 1. So this gives you 2 bonds, no lone pairs. Okay, SN is 2. So how do we get the correct Lewis structure? How do we get the correct geometry, molecular geometry or molecular shape based on these calculations? So let's switch to your textbook, page 136. You would know how to do it. When you look at page 136, that's what you see over here. In this picture, you actually see the steric number. You also see a picture. When you look at this picture, I want you to pay attention. Sticks, this sticks, that means it's bonds. Okay, sticks, that's a bond, that's a bond, that's a bond. Okay, but this rapid year type of stuff with the 2 dots inside, and this is so-called a lone pair. Okay, so when you look at the first one, and if we translate this shape, which is called a linear, and we have 2 bonds over here, so SN over here comes from 2 bonds plus 0 lone pair. And this gives you linear shape. So anything like for example, CO2, we just looked at, when we look at CO2, go back to, if we look at CO2, CO2 has 2 plus 0 as the steric number. So CO2 is linear, okay? And if you look at CH4, we calculated for CH4 the carbon center, as we said, the SN number is 4 plus 0. So SN would be 4. 0 means you have no lone pairs. So this one has 4 bonds and 0 lone pairs. So for this one, you would know it's so-called a tetrahedral shape. Okay. Similarly, let's look at NF3 for NF3 as we calculated, but I'm transferring over here so you can see it more easily. So for this fluorine outer atoms, they're connected to center atom nitrogen. So we just calculated for nitrogen, for this center atom, okay, SN is actually 3 bonds plus 1 lone pair. So 3 plus 1, SN total is 4, but one of this is actually the lone pair, as you can see over here. So it's 1, 2, 3. Look at here, 1, 2, 3. 3 bonds plus 1 rabbit ear, and this is so-called a trigonal pyramidal. That's what you should put down as the shape. All right. We can also look at water. Just give you one more example. For example, if you write the correct Lewis structure for water, it would be like this. You might be tempted to say this shape is linear. It's actually not. We need to look at page 136 and find it out. First, for center atom, this oxygen, actually SN would be 2 single bonds, as you see, 1 here, 2 single bonds plus 2 lone pairs, as you see over here. All right, so it's actually 2 plus 2. This gives you 4. So you refer to this page. That's 4. SN is 4, but only 2 bonds and 2 lone pairs over here. So this shape is called either angular or bent. That's how we figure out the molecular shape based on the correct Lewis structure. We don't need to build a molecular model to figure it out. So that's kind of cool. Let's look at a few more examples so you know how to complete your homework. Let's look at page 137 and work on a few more examples. Okay. In these examples, you're already given the correct Lewis structure, and we ask you to figure out the molecular shape. You need to figure out the name of the molecular shape. So for this center atom, as we see over here, this center atom, so basically look at the center atom. You look at this carbon. This carbon, the SN number, you have 4 bonds, but no lone pairs surrounding it. This gives you 4 total. If you refer to page 136, you would know it's 4 sticks with no rabbit ear type of things representing the lone pairs. So this would be called a tetrahedral. You look at water, you always look at the center atom. This SN number, as I said, you have 2 single bonds, 1, 2, 2 single bonds, 2 bonds plus 2 lone pairs over here. Okay, so 2 lone pairs over here. You add it together is 4. So check page 136. You have 2 sticks and 2 sticks and 2 rabbit ear representing the 2 lone pairs. So this gives you bent shape. Okay. What about this one? I want you to complete it on your own, okay, by checking page 136. Let's look at more examples. Okay. For example, what is the shape for formaldehyde? You look at the center carbon. The SN number is, you look at this carbon, the center has, remember, this double bond is considered as one electron group. Okay, so 1, 1, 1. No dots surrounding carbon. Don't look any further than the bonds and dots directly connected to the center. So you do have 3 plus 0. When you refer to page 136, you do know the shape is trigonal planar. Okay, I want you to work on the next one on your own. Then we're going to move to a few more examples. For the examples you see over here, they have multiple center atoms. When you work on multiple center atoms, look at each center atom once at a time. So basically, for example, for this example, ethylene, you look at carbon A, and you only look at the bonds and the dots that is connected to that particular carbon, and do not look at anything further than that. So for this carbon, when you look at it, on the left side, you have 2 single bonds, and on the right side, you have a double bond. So 2 single, a double. Remember, a double is also considered as 1 electron group, and no dots surrounding this particular carbon. So Sn for the left side is 3 bonds plus no lone pairs. This gives you 3. Refer to page 136. That will give you trigonal planar. That's what you write down over here. Trigonal planar shape. When you look at the right side, okay, when you look at this carbon, it's the same way. The SN number, you have a double bond. Now this double bond and the 2 single bonds over here. All right. So look at that. It's this double bond and this 2 single bonds. So Sn is 3 plus 0. No lone pairs. That's also 3. So B is also trigonal planar. To summarize this, in order to get the correct molecular shape based on the Lewis structure, you look at the center atom and figure out the number of electron groups, calculated by calculating the number of bonds plus the number of lone pairs. Then refer to page 136. You have the correct molecular shape. For multiple center structures, you look at each center at a time